All right, welcome back, everyone. So today I want to share a few things I think I've learned about multi-agent collaboration from studying how humans play video games. In particular, I'll focus on a fairly chaotic online multiplayer game pictured here called Bleeding Edge. But I've personally been involved in replicating the findings here across a far wider range of games, some of which are pictured here. Most of these games were clearly multi-agent, but even those that appear single agent have always required some form of human AI interaction. That's been the core fundamental problem across my entire career. Um, for the sake of today, given the time that we have, and because of the recency of this result, I'm going to talk about this particular game here. So this is a game called Bleeding Edge, made by Ninja Theory, a Microsoft game studio based in Cambridge, very close to the lab that I was in at the time. In collaboration with them, we had access to a large data set of human gameplay from this game. So this is a team-based game. It's played online. You have two teams of four players that play either in a sort of capture the flag style mode or a king of the hill style mode. The main thing is that this is two teams of four players playing against each other, and we have a lot of human data. For this particular paper, we used 8.6 years if you rolled it out in real time, but we had access to a lot more that made this possible. At that point, I should really stop to emphasize that a project like this is absolutely not my work. It's down to the amazing team that I had the privilege to work with at Microsoft on this. And all our past colleagues and external collaborators. Like, none of this would be possible without the wonderful people up here. And if I say anything smart, it's because they taught me it. And if anything is wrong in this presentation today, it's entirely my fault. So please call me on it. I'm still here to learn, okay? But I can say nothing but wonderful things about these people and thank them for giving me the material to present this today. So to formalize the core problem, the thing that I like to think about in human AI interaction in particular is ad hoc teamwork. And this is the skill of being able to jump into a game and pick up and play with any other person. And in particular, I find this is really useful to study in video games because people do this regularly. So in a lot of games, you will be randomly matched with other people online, and people regularly pick up and play well with each other. I want to take the assumption that we're at a point where we can train agents to play reasonably well together on a particular game. So two agents can be played well together. And I think we can repeat that process and train other agents to play well together. But one of the big problems, particularly in the deep RL period of overfitting, was that you could run this twice and those agents could play well on those two separate teams, but they rarely played well with each other. So they're very much overfit to their teammates. And even worse than this, it could be two instances of exactly the same algorithm, but trained two separate runs of training, and then they've converged to different equilibria and they're not compatible. So the players then play well together. This problem was proposed in the AAAI 2010 paper by Peter Stone and colleagues. I think there's some earlier work even by Michael Bowling. I took a lot of inspiration, particularly from this paper and the work of Peter Stone's lab. To formalize this more, essentially we are extending the normal multi-agent MDP objective to include an expectation over the other possible agents. I will break that down a little bit more, because I think whilst it looks like a scary math equation, it can be separated into three quite conveniently explained topics. So first of all, we have the policy that we're trying to learn. We have the policies that we expect to play with. And then we have the reward that we want to maximize. Stay free of RLDM. So I'm hoping we can all agree that this is probably going to be learned by reinforcement learning. And to simplify things, I'm going to assume that the reward we're trying to maximize in this game is the team score. I don't think that's necessarily the best objective to maximize for human AI interactions. And I have a lot of opinions about whether we should have a single reward, but I should probably focus on the topic for today, which is going to be modeling the human play and the policies that we expect to play with. Now, again, I think this is of critical importance in a multi-agent learning setting where you're going to interact with human players, because of this work particularly inspired me, and I think some of the authors are here, Mark's around somewhere. So this is work from Berkeley on the overcooked clone. And what we can see on the far left is that when a self-play agent plays with a human player, then the self-play agent, even though it plays well in self-play, stubbornly pushes against the human player with the green hat and makes the human player adjust. Now, that is not the player experience that I want to give or have that interaction with the AI. So in this case, there is a learning agent, and it's the human, and the agent stubbornly forces the human to learn to adapt to its policy. Whereas in the work, they showed that if you imitate human behavior and learn a best response to the human behavior instead, then you can get some policies more like the ones on the right, where they play nicely and can actually adapt to humans playing in different styles. That's the sort of experience that we want to go for, where the AIs are adapting and supporting the human players rather than the human player having to adapt and work with the AI. Right, audience participation time. So to get started on this game, we wanted to first sort of simplify down and isolate a simple single agent task to check that our reinforcement learning framework is set up well, and start thinking about how we're going to evaluate whether we are emulating human play. So what you're going to see in a moment is either a human or an agent moving from the same start location to the same goal location. One of these is a human, one of them is an agent. Okay, let's start playing it. As I said, this is a quiz. You will be assessed, and I am watching every single hand in the room. So watch the videos closely. Have a think. Which one do you think is the human? This was a study that we ran online during the pandemic. We wanted to have a way to sort of get people to interact with this, so people could like scrub back and forth through the videos and look at these in time. Okay, let's do some hands. Who thinks video A is the human? A. You were slow there, I saw it, but you went A. Okay, who thinks video B? Okay, it's kind of split. I think A was the more confident. I see the late vote for B there. But yeah, I think A was winning out slightly there. The answer is A. A is the human. And to this particular agent, the B agent, was based on some prior work that was right around the same time by Elwar Alonso and colleagues at Ubisoft. PPO, we discretized the action space. It did have some symbolic state at this point, and there was also a variant that had like a symbolic state plus a depth map there. The reinforcement learning curves look good. It approached human times on getting to the goal. So as an RL person, we were quite happy, like our curves go the direction that we want them to, yay. But we showed it to a lot of humans on the internet, and they didn't agree so much. So in a moment, I'm going to show what the humans voted. If the dots are below the line, that means the agent was judged as more human-like. Dots above the line say human was judged as more human-like. And people could reliably tell the difference. And I'd say the majority of people in the audience here today also saw it. And in fairness to those that picked B, in the actual study, people got to scrub back and forwards and judged many of these. So they had some more time to pick up those differences. But yeah, human observers could readily tell the difference. And this isn't too surprising, right? Like it's just been trained on reward maximization to get towards the goal. There's no bias in that towards it actually acting human-like. So it's just running towards the goal quickly. We did have a free text entry in the survey as well for people to describe how they were telling the difference. And there was quite a lot of consistency in the particular behaviors that were giving away that this was an agent and not a human. And so as a reward hacking, reinforcement learning, engineering type person, I just stuck all that information into the reward, and you get an agent that confuses humans. That That's not really ideal. We don't want to have to do an online assessment for every agent's walking style to get that knowledge and hammer in that knowledge via the reward function. But it worked, and it got us to one that confused the human annotators. Instead, ultimately, what we wanted to find was something that was a more generally applicable approach. And possibly no surprise, we use imitation learning. And in particular, we're blending reinforcement learning and imitation learning together. I really, really like this mix, particularly for game playing, okay? And we can talk maybe about it not applying to things outside of video games. But if you've got a clear reward signal, I do think that these two go really well together for creating human-like behavior in these environments. As the imitation learning is a good prior, a better prior than like a maximum entropy regularization for human behavior than that you'd get in a lot of these deep RL algorithms. And also the pure behavior cloning imitation learning that we were using won't do very well online because it gets out of distribution. We've got lots of classic arguments about this and the theory to support it. But if you blend it with some RL, the two together complement each other really nicely. And so when the imitation learning agent gets out of distribution and starts acting non-human-like, the RL agent is steering it towards reward maximizing, which gives it something of a nice behavior. And so here's the final agent. The video plays quite slow on this one for some reason, but this was a much smoother experience, and this completely confused participants. This actually led to a really interesting discussion as to what did it mean to actually pass this test and this evaluation. So the reward shaping agent completely confused participants as to which was the human and agent, whereas the final agent was more often, it was considered more human-like than humans by the majority of humans. So people were like discriminating, but they were incorrectly classifying which was the human. So we went back and forth on this a lot as to whether you wanted the one that was that you were unable to tell, or the one that was more human-like. But that's a rabbit hole. The main point here is that these deep RL agents could learn efficiently to navigate in the 3D environment. The high skill alone was not enough to reproduce human likeness, but because people were quite consistent on this, we were able to get to a mix of behaviors that could do this particular task. Now, that's a very, very small part of the game that I showed. That's just a single agent navigating around. The full game is far more complex mechanics, and we were now starting to have access to that much larger data set. So we want to start scaling up, and we want to start bringing in the full range of human data for the full game that we have. And in particular, and perhaps not surprising to the RLDM audience, human data is not agent data. Right? There are huge differences, particularly when you get 8.6 years of human gameplay data. It is not enough to just imitate a single behavior. And a lot of common assumptions from the dry side in the imitation learning work are that trajectories are generated by a single policy. The policy is an optimal reward maximizing agent. And the policy, which one did I miss? It's hard to look at the screen from down here. It's like massive. The policy, yeah, and the policy is fixed throughout data collection. I lost track of this time of how many papers from the computer science literature that were like, we generated these trajectories from this little network, and now we can imitate it with exactly the same little network. Well, of course you can, because you knew what the function was that was generating the data set, and now you managed to fit it again with the same function. We don't know what the function is that is generating this human data, and that's half the problem. We also, when we get a data set like this from a game studio, it is a big mess, right? Like there are instances where people have put the controller down and aren't doing anything. There are labels of whose data it is, like which anonymized player ID it is. But you have no idea who held the controller at the time, or that the cat jumped on them, or anything like that. That's completely invisible, and we don't know what's going on in the environment or who is even providing that data set. This is a little bit of a straw man. Of course, there are papers that break some of these assumptions, and I'm looking for recommendations. I'd love to hear from people in the audience throughout the rest of the week if you've got recommendations on papers that break some of these assumptions. But one of the ones that we took for this was a piece of work we published at iClear 2 years ago. So the previous paper had shown how we imitate a single agent's behavior and replicate a single particular behavior. But what we really want to do is emulate the full diversity of human play, every single way that they possibly play in a single model. To do so, we first considered this arcade claw game that hopefully everyone's somewhat familiar with. So we assume that there's like a snake toy and a ball that the player might want to get. The ball is nicely circular, but the snake is a really awkward distribution. And so if we look at the sort of the data from human participants that successfully capture this, they get this sort of coverage. Now, if we do the sort of behavior cloning mean squared error approach that I did on the first paper, we would learn this policy from that data that is absolutely useless and collects no toy. It represents one average behavior. But what we did by using diffusion was we're able to get much more coverage of the full complex joint distribution. In particular, the year was 22, the sun was out, we were starting to get back out again, and there was a lot of hype for the stable diffusion DALI imaging models at the time, having a lot of success modeling these sort of complex joint distributions. And so we just changed that around into a sequential decision-making setting. And instead of text to image, we did observation to action. And we found this highly effective for modeling multimodal behavior in our data sets. I'll show an example here from a robotics simulator, mostly because we have tended away from using the diffusion approach for these games. Research isn't linear. This was one pathway we were exploring. We didn't find this was as critical for the games, because in the games, we could often discretize the action space and that was sufficient. Whereas in, I believe these approaches are more commonly used still in the robotic space where we don't want to do that discretization. But for the games, we could often discretize, and then we could still get the multimodality without having to go to diffusion. But yeah, this was still really successful for somewhere where you really need continuous control. Instead, if we're going to discretize actions, around that time, there is another model that is very popular and effective for modeling large sequences of discrete data, and of course, that's transformers. And so in the parallel thread, we were exploring how to use transformers, and particularly finding this useful as a way that could actually scale. And so we, in this paper at NeurIPS, we take a very simple approach. Essentially, our data set is a sequence of observations of the screen, actions taken, and maybe some metadata about the game, like the score at the time. And we can just put that through a big transformer. More interestingly, if you actually think about this as a bidirectional transformer and masking, you can actually pull back a lot of sequential decision-making tasks in a single model. So we were doing behavior cloning. We were thinking about, like, we've got a history of observations and actions, and we want to predict the next action. But at the same time, there was a lot of work in doing offline reinforcement learning with these models. So you take the reward to go, the reward you want to get, and the current observation, you say, what action should I take? But if we do a bidirectional model, we could also do goal-conditioned imitation and say, I've been in these states and I want to get to that state. What should I do next? And that doesn't have to be one step ahead. It could be like waypoints, and we could say, I'm here, I want to go over there, then I want to go over there, and it can fill in all the gaps. We can also think backwards and do inverse dynamics and say, I took this action, I'm in this state, where did I come from? Or even further back, like, what action did I take before that, and where was I coming from? Similar for forward dynamics. So you can start to think about sort of a world modeling objective that I'm in this state and I took this action, what's the next state? Or even further forwards. And the big thing here for us was, like, with a big transformer and enough data, we could just train one to do all of these. And for the NeurIPS paper, it worked in a grid world, and it was particularly effective to do this. And it was better than bespoke models trained just to do behavior cloning or just to do forward modeling. So this I don't know, this was kind of a fun result to see that we could do this many things with one transformer. Disappointing in a little way that those transformers have worked again, but it was it was a very useful tool for us. And it's a good one. Does it go? Is it going to scale to our full data set? And so we put the analysis in on to doing scaling laws, and we found we could get similar sort of scaling laws as you get for large language models, but instead for imitation learning and world modeling objectives. And in particular, this was effective for the world modeling objective, more so than the imitation learning, because the loss for behavior cloning does not necessarily correlate with the actual performance in the game. But the loss for the world modeling objective did correlate nicely with the fidelity of the footage that was generated. So we have a training recipe that can do many different objectives in a single model and seems like it's going to scale. So what would that mean for a game like this? Well, I could ask, what action should this player do in this situation? Or I could say, where has that player come from? And this is where we start to get back to the ad hoc teamwork setting. So now there is a model, there is an implicit idea within this model of what others are doing in the environment. Similarly, where has this player come from? What are they going to do next? Slightly conscious on time, so I want to get to some of the videos on this. What we ended up doing wasn't the bidirectional transformer. Again, for scaling purposes, it was more practical to use a causal transformer. We first discretized our images with a VQ-VAE, and then we used that as a sequence to sequence for a causal transformer of images and actions out. And we called this WAM, our world and human action model. So it's not just doing world modeling, it's also doing the human action modeling as well. And we pushed this up to 1.6 billion parameters, trained on 112 H100s for 80 hours. This model can't do all of the things that the grid world one could do, but it could do three things that were very useful for us. One is that it could do the behavior cloning objective, so it could model the diversity of human play that we wanted to recreate. And the really shiny thing that we got attracted to was that it could do world modeling as well. You could actually play the game inside this model. And you can also go into like a full automated video generation model mode because it's also predicting the actions. So you can just set this thing into an automatic mode, some of which I'll show in a moment. So this is an actual screenshot from the game. That's the player's character in the middle of the screen. And this is a picture of another character that wasn't there that we dropped in with Microsoft Paint. Of course, it's good Microsoft employees. This actually is quite good. Like we got really good at copying and pasting images onto the top of screenshots. Like that's much smoother than they were at first. Before they had like big gray backgrounds on them. But this is all we've done is we've taken a screenshot from the game. This is not a screenshot that the model was trained on, and the model definitely didn't see that other player there before because we just made it up and drew it on ourselves. And what you see when the video mode goes in is that the other character on the screen actually acts out and starts to fight in the scenario. And this is the model that I mean, that is like this implicit behavioral model that is in there of opponents. I'm not here with answers. I have no idea how we're going to use this to improve our ad hoc teamwork agent, but I'm really curious now about the fact that we have this big model that like, do we need to have a disentangled model of the human when we can do such counterfactual reasoning over what would happen if there was an opponent in this location or if there was someone here? To give one more example before try to wrap up somewhat on time, I think. Yeah, okay. Here's another scenario, again, screenshot from the game, not in the training data set. We copy and paste our person on, and now we see a very different behavior. Hopefully this isn't too blurry. So last time the character dropped in, he was really aggressive, he went into attack. And this time he runs away, jumps out the window at the back. So yeah, I'm super curious like how we use this now back in this framework. So one of the other results we have in the paper is we show that the behavior cloning side does model the sort of full diversity of play. But also now, how do we use that world model and that, whilst it's like a really messy model of the human being entangled in it, like how do we use that world model in improving our agent's ability to do ad hoc teamwork? I won't go much more into world models, as there's going to be like a whole session of them later on. I know Tim's somewhere, and there's some stuff from Matteo Netti's group as well this afternoon. So just something to keep in your mind when you're watching some really good world modeling talks this afternoon. In particular, the approach the approaches I've talked to about today are all very complementary for this goal of modeling the policies that we expect to play with towards the grander goal of ad hoc teamwork. And so what we've talked about is having a scalable backbone with the transformer. We find this is very useful, scalable backbone for modeling many different objectives and sequential decision making. But we can, if we want, add a diffusion layer to this to capture more sort of multimodal behavior. In our experience, that was particularly useful for continuous control more than discrete, but experience can vary, and particularly for the world modeling thing, the world modeling loss, there's a lot of really good work out there showing that diffusion is helpful for the world model. And we started off with some of our work on evaluation that's useful for us as we judge and assess this. And again, we used a lot of that sort of qualitative assessment and framework and methodology as we evaluated our world model and agents at the end. Here are the papers. And I'm proud to say that, like, for all of these are all open source, open data. We've all got permissive license on them, so people can continue to build on this and hopefully teach us more about what we could do with these things. Thank you.